So hi everyone, I welcome you all to this sixth lecture in which I will be going to continue the discussion on mechanical properties of fluids, and that is essentially a fluid mechanics mainly. So yesterday I end my lecture with one of the question. So let's discuss that first. So that question is I gave one question. So that is a cubical container with side L is completely filled with water. Calculate the horizontal acceleration of the container so that the half of the fluid will come out of the container. Okay. So we need to solve this question, and so let's solve this question. I hope you tried this. So we have a cubical container that is at t is equals to 0. It is filled with water, let's say. So the side is L. This is L. This is L. And this is L. This is one side. So that's a cubical container. And let's say the acceleration is in this direction. So if the acceleration is in this direction, so I have already discussed that what will happen if the acceleration is this direction, we will be having a shape of the interface something like this. So when I'm taking a 2D picture of it. So this is at t is equals to 0. At some times t, half of the fluid should be spelled out. So half of the fluid should come out from the container, and in order to do that, so it is very clear that if it is accelerating in this direction, then the interface after t time will become something like this. Okay. So but the question is whether the interface, so we need to find out the angle of this so that uh, we get to know that what we need to find the a, because tan theta is nothing but a by g, and we need to find what is a. Okay. So if you see this from this figure, we cannot say that uh, half of this, so this is not half of this total fluid. To spell half of it, we need to cut it uh, at 45-degree angle. So in order to do that, it should be like this. Now we can say that half of the fluid is spelled out and half of the fluid is there. And this become theta is nothing but we get to know that is 45-degree. And so tan theta is 45-degree. So it comes out to be, A comes out to be equals to G. If you cannot interpret with this way, that just by a simple reasoning that how it comes 45-degree, then what we can do is we can find out the volume. And let's say the volume, if it is H, let's say this is H, this is L, we know this is L, and let's say this is theta. So volume came out of, we need to find out what is the volume came out of it. So what is the volume here? If you see, that is 1 by 2 into H into L into L. So that is L square. So that is the volume here. So that is H L square by 2. So the total volume, initial volume is L cube, initial volume at t is equals to 0. R t is equals to sometimes t. It becomes, we want to find out L cube by 2. So this should be equals to L cube. So L cube by 2 should be equals to H L square by 2. And from here we can get H should be equals to L. And we know when H is equals to L, then tan theta is H by L, then it is L by L, and that is 45-degree. So if you, this is when if you are unable to interpreting it with reasoning, so you can go with this way. So what we did is we calculate this, we find this H, what should be the H, so that the volume that is remaining in the container is HL is uh, the volume that is spelled out is half of the volume of this. So that is L is cube by 2 and theta is 45 degree, and then when theta is 45 degree we get the same answer. Let's take one more question, one more simple example to that. Now if so the solution to this is G. Let's say the question is find out the acceleration of the cubical container of side L containing a fluid containing a fluid in half of its volume and one third of the fluid should come out of the container due to acceleration. Now the question is, we have this container, and if it is a cubical container, so I can copy this. Okay, that's a similar question, but now the fluid is not completely filled. The fluid is filled half. Fluid is already half. So that is, the one thing is very clear, that is fluid at T is equals to 0. The volume of fluid is L cube by 2. Now one third of the fluid should come out of the container due to this acceleration. So one third of the fluid come out. So if it is accelerated in this direction, in the same way, we have this kind of shape of the meniscus, and so now this is H, this is L. So this much of volume will is come out of the should come out of the container due to the acceleration, and this is nothing but 1 by 2 into H L square, and that should be equals to L cube by 2. So one third of the volume, one third of this volume, that is 1 by 3, and from here H comes out to be L by 3. So H comes out to be L by 3. So tan theta is nothing but H by L, and that is A by G. So A by G is 1 by 3. So A comes out to be, sorry, uh, yeah, so A comes out to be G by 3. So let's take another concept. You can say on a similar way. So now let's say operation in a rotating cylinder. So we need to calculate the pressure in the rotating cylinder, pressure distribution basically. So let's say we have this cylinder. So we have this big cylinder, and let's say this is, so this is the center line, and this cylinder is rotating, let's say with angular speed omega. So what will happen is, if there is a fluid like this at T is equals to 0, so if this is at T is equals to 0, then due to the rotation it comes like this. If this is the radius R, so there is a depression at the center due to this rotation and force balance. So let's balance the force. So shape of the the shape of the interface will become like this. And so if this is R, let's say this is Y, or I can take inside this. So this is Y, this is theta. So then theta is nothing but dy by dr. And because we are rotating this, so according to pseudo-force, so this, if we take this particle here, so the F net will be like this. Here it is the mass of the fluid, that is mg, and here it is the force due to the acceleration, angular acceleration, that is m r omega square. So if this is theta, this is theta, this is also theta, then tan theta will become m r omega square by mg, and that is r omega square by g. So dy by dr comes out to be r omega square by g. If we need to find out the pressure at this point, we need to find h and y varying from 0 to h, and r is varying from 0 to r. So dy 0 to h becomes r omega square by g, dr 0 to r. So h comes out to be r square omega square by 2g. Okay, so that is the height. And now we can easily calculate what is the pressure at this point. So we can easily calculate the pressure at this point. So the pressure at this point is P naught plus rho GH. So pressure at this point A is P naught plus rho GH. So P naught is the atmospheric pressure plus rho GH, we know R square omega square by 2G. So PA comes out to be P naught plus rho R square omega square divided by 2. So in JEE one question came, so I will be discussing next that that question next. So that question is, so the question is, a long cylindrical vessel is half filled with a liquid when the vessel is rotated about its own vertical axis. The liquid, I don't know the year, the liquid rises near the wall. If the radius of, if the radius of vessel is 5 centimeters and its rotational speed is, its rotational speed is 2 rotation per second, then find out the difference in the height between the center and the sides of the, between the center and the sides of fluid will be. Options are 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter. I will discuss the solution to this question in the next lecture. Okay, just try this and let me. Okay, now the next questions are next concept that I will be going to cover is the pressure measuring instrument. So there are pressure measuring instrument. So there are many pressure measuring instrument, uh, pressure of atmosphere or atmospheric pressure, pressure of gas in a vessel. This is the instrument used to measure the atmospheric pressure is nothing but barometer. The pressure that is used to calculate the gas stored in a particular vessel, that is manometer. Apart from that, there is a YouTube, some questions on YouTube that generally comes from the exam based on the same concepts of weight balance or the pressure balance. Okay, so I will be going to discuss first barometer. The barometer, it is invented by Torricelli that will be used to measure the atmospheric pressure. Okay, so what he did is uh, he take a mercury in a container and put it at sea level, and then he took one tube like this. So one tube is taken. So we uh, put a thumb over it. The thumb is, we put a thumb here so that there shouldn't be any air inside it, and we put it here. So this tube, he puts it here. So what will happen? Mercury will rise. In the surrounding, it's P naught, that is the atmospheric pressure at all the points. And he put this and find out that there is a rise in the mercury. Let's say it comes out to be H. So P naught, he balanced out the P naught and because the pressure along the horizontal line is same. So P naught at this should be equals to, let's say this is 0.2. So P naught should be equals to P2. P naught is atmospheric pressure, P2 is rho G, height of the mercury that is rise. And inside that is vacuum, so there is nothing there. And he found out that the height of mercury at sea level is 76 centimeter. So that is at sea level. So P naught from it can be calculated as, we know the rho of mercury. Rho of mercury is 13600 kg per meter cube. So 13600 kg per meter cube into G10 into 76 divided by 100, and through it we get P naught to be 1.01 into 10 to the power 5 Newton per meter squared. That's the experiment that he did. From this experiment, we get to know what is the height of the mercury rise. So this is from the experiment. We get to know this H, and from there we get the atmospheric pressure. You may ask a question that why he has chosen mercury. Why not any other fluid? And why in general in when we calculate pressure, we generally say it's 76 centimeter of mercury, something like that. Why? The question is why mercury? So mercury is because it is having a high density liquid, hydrophobic, like mercury, glass, contact angle is around 135 degrees. Opaque and shiny. Opaque and shiny means that you will be able to see that brightness. So that is shiny in nature. Phobic that it will not going to get easily vaporize. And okay, so this is about a barometer. Let's take one question. So the manometer is tilted. Sorry, barometer. The barometer is tilted and it makes an angle of 30 degree with the liquid air or with the edgy air interface. The height of mercury in the barometer in the tilted barometer is 100 centimeter. Find out the atmospheric pressure. Options are the density of mercury is 13600 kg per meter cube. Options are 70,000, 68,000, 136, none of them. What I do is I just go through this question and try to solve it. The barometer is tilted at 20 degree with the mercury air interface. The height of the mercury in the tilted barometer is 100 centimeter. Okay, we know the height. So what's the difficulty in this question? There is no difficulty. Height is 100 centimeter, that is given. And pressure is, how does it matter if it is tilted or not? We know what is the height of the barometer, that's it. So that is 100 centimeter. And P naught comes out to be 100 into 10 into density of mercury, that is 13600. And this is 100 centimeter into 10 to the minus 2. Okay. So it comes out to be 136,000. One minute. I did one mistake here. That is in Pascal. Okay. The correct option is this. You know? Why not? But my dear, this is the wrong way of doing. Let's read the question. The barometer is tilted and it makes an angle 30 degree with the mercury air interface. So when we are reading, at least we should try to make a figure of it. So if it is this, the barometer is tilted like this, and it makes a 30 degree with the interface. If it is tilted like this, if it is this anyway, this will not going to be the angle that is 30 degree. And he said that height of the fluid in this is, so this height is given, that is 100 centimeter. But I told you in the lecture that we cannot calculate this height. We are only interested in this height. So P naught should be rho g H1, and H1 is not 100 centimeter, my dear. And so what is H1 is? So H1 is sine 30 is equals to H1 by 100. So H1 comes out to be 100 by 2, that is 50 centimeter. So this is the correct height because I told you that the pressure does not depends upon the shape, my dear. Okay. So the pressure here is comes out to be 50 into 10 into 13600 into 10 to the minus 2. That's because of centimeter. That comes out to be 68000 Pascal. So that is the correct way of doing, and the option this is wrong. Correct option is this. Okay. So now let's discuss next measuring instrument, that is manometer. That is a very important instrument in the engineering applications because where we need to calculate the pressure of a gas inside a vessel, we have to use the manometer. Okay, so let's say we have a gas filled in this volume, and manometer is something like this. I want to make out one point here is that in case of barometer, this is experimentally calculated, that is for mercury. You can take any other fluid also, and accordingly the things will going to change with the density. Okay, there is a gas and it has obviously some pressure, and manometer is also open to atmosphere. So let's say there is a fluid, let's say mercury inside this. So let's say mercury is there, and due to this, because it is connected to a gas, there is some rise in the fluid. If it's a vacuum, then these levels are same because pressure will be zero. So that is a gas here. And if I have to calculate the pressure at this point, this is H. So pressure here is, let's say P1, here is P2. Because along the horizontal line there shouldn't be any change in pressure, so P1 should be equals to P2, and P1 is the pressure of gas, and P2 is the atmospheric pressure P naught plus rho G H. H. That is the height of the fluid. So this is the way manometer works, and this instrument is having a high applications. Some question will come on this. You may go through it. I will not going to discuss any question here, but this is the way that how manometer works. Okay. Another thing is we have a YouTube. Some questions will come on YouTube. YouTube is a bit important. So it's a movable boundary. Let's say YouTube is divided into two fluids. So some questions I'm directly going to discuss the question. So it's the movable boundary. And let's say there is some fluid at t is equals to 0. Movable boundary is in the way that the two fluid should not mix, otherwise they will flow, they will push each other. That is another fluid. Let's say this is 10 centimeter. This is also 10 centimeter. So this is the configuration at t is equals to 0. The density of this fluid is 1 gram per centimeter cube. I am calling this rho 1. The density of this fluid is rho 2, that is 5 gram per centimeter cube. So if I, after some time t, what do you think what will happen? The denser fluid will try to push the lighter fluid in one direction, and due to which there is a shifting in the height. There will be a shifting in these heights. Okay. So what will happen is there is a very nice question came in JE on YouTube. I will be going to discuss that soon. So at some time t is equals to t, what will happen is I will make a copy of it. Otherwise it will take this out. Okay. Now, so what will happen is this this is heavier fluid. This will go this will shift here. This will go down and this will rise up. This will rise. This will be rising up. So let's say it shifts x, then it will be also x, and this will go here. This will also the mover boundary shifts here. So now we need to find x. The general question is what is x? So what we do is we will take this line, horizontal line, and calculate pressure at this point and this point. Because we know that pressure will not going to change it in the horizontal direction. When I'm saying this, pressure is not going to change in horizontal direction, you have to think about it. For what conditions? For the current conditions, it is not there. But there may be a possibility when there is a change, when it is an accelerated fluid that I have already discussed. So you have to keep those things in mind. Don't listen to me vaguely. So if I call this point A and if I call this point B, so PA is, I will take another pen. Okay. So PA is 10 minus x into rho 2 into G. Okay. PB is 10 plus x into rho 1 into G. And to achieve the out each other. So PA equals to PB because we know that pressure will not going to vary in horizontal direction. So 10 minus x into rho 2 into G should be equals to 10 plus x into rho 1 into G. So G will cancel out. 10 minus x, rho 2 is 5. 10 plus x, rho 1 is 1. 50 minus 5x is equals to 10 plus x. 40 is equals to 6x. X is equals to 20 by 3 centimeter. Okay. So let's discuss one question that came in JEE 2014. So there is a circular tube in a vertical plane, two liquids of density D1 and D2 are filled in the tube such that each liquid subtends a angle of 90 degree at the center. We need to find D1 by D2. Options are 1 plus sine alpha divided by 1 minus sine alpha, 1 plus tan alpha divided by 1 minus tan alpha, 1 plus sine alpha divided by 1 minus cos alpha, 1 plus cos alpha divided by 1 minus cos alpha. So take 2-3 minutes, try this question. I know that it will not, you may not able to grab that question in 2-3 minutes. But after 2-3 minutes, I will be going to discuss the solution to it. Try whatever you wanted to try and see what will happen. Whether you will be going to get some similar solution, at least similar to some options. So I will make the figure of this question. and discuss the solution. There were two fluids like this, another fluid here. Okay, and alpha is this angle. This is D1. This is D1, and this is D2. The radius of this circle is R, that is outer periphery. That is R. So we need to find out the D1 by D2. So I forgot to make the figure. So but now I have to discuss the question. So I'm going to discuss this. So let's take one horizontal line so that considering that the pressure at that point will not going to change, and we should balance it out. And we know that pressure is independent of the shape. For this fluid, this is there. So this extra term is going here. So that should be that will become negative. So that for due to this, the fluid one, the pressure become negative. So if you want to make out a balance at this point, so this is so let's take this another line. So we know this is R, this is also R, and this is because we know fluid substrate 90 degrees, so that is 90 minus alpha. If this is 90 minus alpha, then this distance is R minus this one. So that is R sine alpha. That is perpendicular. R. So this is perpendicular upon hypotenuse. So that is R minus R sine alpha. From here it comes out to be R sine alpha. Let's calculate this. So this is nothing but this is. So here it is, this distance is R cos alpha, and this complete distance is R. So this become R minus R cos alpha. For this fluid, so we know this distance is nothing but R minus R sine alpha, and this distance is, we need to calculate this distance, and that is nothing but R sine alpha. That is by geometry. So if you see this line, this horizontal line from here, sorry, this is R sine alpha. So this is alpha, this is 90 degree again. And so you get this to be R cos alpha and R sin alpha. So that is alpha, that is this distance is R cos alpha, this is R sin alpha. That is R sin alpha plus what about this remaining distance? The remaining distance is this distance is from here to here, this distance, where this fluid is present. So that is this distance is R cos alpha. So here in this height the fluid is D2. So now we need to balance out here. So it comes out like, so let's say pressure due to this, whatever this is, P naught. So P naught plus rho, so D1 into G into R. R I will going to take common. 1 minus sine alpha. That is a bit tricky question. And it came in JE means 2014. At that time, I also unable to solve this question. So now here it's P naught plus d2g r sin alpha plus cos alpha, and this part minus, sorry, plus d1g r into 1 minus cos alpha. From this equation, we will be going to get the solution. We not cancel out each other. So let's take d1g together. So g also cancel out, r also. So what we get is d1 together 1 minus sin alpha minus 1 plus cos alpha is equals to d2 sin alpha plus cos alpha. Okay. So d1, this will cancel out. So cos alpha minus sin alpha, cos alpha minus sin alpha is equals to d2 sin alpha plus cos alpha. So we need to calculate d1 by d2. So that comes out to be sin alpha plus cos alpha divided by cos alpha minus sin alpha. So there is nothing like this. Only 10 term is there. So let's divide it by cos alpha. d1 by d2 comes out to be tan alpha plus 1 upon 1 minus tan alpha. Correct option. So for your understanding, I'm repeating that what we did. So what we did is, because we know that pressure is independent of shape, so we need to find out this height to balance out there here. From here, we need to find out the pressure here. So, or you can say that we are calculating pressure here due to this and pressure here due to this. So we are calculating pressure and we are balancing out each other. So here two fluids, height of this fluid is and height of this fluid is there. So net height of this fluid is r sin alpha plus r cos alpha. How it comes is, this is r, this is alpha, so that is r. This is r cos alpha, this is r sin alpha, so this is r sin alpha plus r cos alpha from coming from here directly r cos alpha. So I sin alpha plus r cos alpha plus, so this fluid, now the fluid is changed. So this is, so the net height in this direction is, if you see, that is r sin alpha plus r cos alpha due to fluid 1 and r minus r cos alpha due to fluid 2. Here it is r minus r sin alpha. Okay, so we balanced out each other, and what we get is, we calculate the pressure at this point, at this point, and we know that both are equal, and so we calculate pressure at this point and this point, and both are equal, and from there we get the solution.